Up to this point in the class, we've discussed individual feedback control loops. Typically, a single unit operation may have multiple feedback control loops for multiple controlled variables. Therefore, it is important for us to consider how process control strategies are implemented at the process unit level. And that's what we'll be doing in Chapter 13 of the Seaborg text. First, we'll introduce the concept of the degrees of freedom for process control, or the control degrees of freedom. Next, we'll discuss how we choose controlled variables and manipulated variables. And then we'll also discuss selection of which variables to measure. We'll conclude with an in-depth example of an evaporator, and then we'll take a look at 3 other interesting examples that are presented in the Seaborg text. To understand the concept of control degrees of freedom, consider this model of a heated tank with constant volume overflow. The model for this heated tank shown here contains only 2 energy balances and a relationship assuming that the temperature of the heating medium, which here is steam, labeled T sub S, is a function of the steam saturation pressure, P sub S. In this version of the model, we've already used the steady state material balance to set Wi, the inlet mass flow rate, equal to W, the outlet mass flow rate, so that Wi could be eliminated from the energy balance for the fluid in the tank. This says that the accumulation of thermal energy in the fluid contained in the tank is equal to the difference between the thermal energy entering and leaving in the process streams, plus the amount of thermal energy that's transferred from the heating coil. There's a separate thermal energy balance for the heating coil that describes the temperature of the tube wall. The first term, on the right-hand side, accounts for the thermal energy provided by the condensation of saturated steam inside the tube, and the second term accounts for the transfer of thermal energy from the outside of the tube wall to the process fluid. Each of these thermal energy transfer processes has its own heat transfer coefficient and surface area, H and A, over which it's occurring on the inside and the outside of the tube wall, respectively. We might assume that ρ, V, the process fluid heat capacity C, as well as the mass and heat capacity of the tube wall, and the heat transfer coefficients and corresponding heat transfer areas are all constant known parameters. The variables then, the things that can change with time, might be the steam temperature and pressure, the process fluid temperature in both the effluent and inlet streams, the tube wall temperature, and the mass flow rate of the process fluid, W. With 6 variables and 3 equations, this model has 3 degrees of freedom. That is, because we have 3 equations, we can predict 3 of the 6 variables, probably the steam temperature, the process fluid effluent temperature, and the tube wall temperature, because those are the variables that our equations are solved for. And the remaining 3 variables need to be provided as inputs to the model. Those input variables must be the inlet fluid temperature Ti, the steam pressure P sub S, and the process fluid flow rate W. The number of control degrees of freedom is the number of process variables that can be controlled independently. Often, this is the number of independent variables that can be manipulated, but it is given by the number of degrees of freedom of the model minus the number of disturbance variables, N sub D. In this case, we may have 2 disturbance variables, the incoming temperature of the process stream, Ti, and the process stream flow rate, W. If both of those variables are disturbances, they must be subtracted from the number of degrees of freedom to determine the number of control degrees of freedom. Assuming that Ti and W are both disturbances, then we have only one control degree of freedom. And that control degree of freedom must be provided by one manipulated variable, in this case, the process steam pressure, which would be controlled by regulating a steam valve on the steam supply to the coil. What does it mean here that we have only one control degree of freedom? What it means is that only one of our 3 output variables, Ts, T, and Tw, can be controlled independently using our one manipulated variable, the steam pressure. If we choose, for example, we could use the steam pressure to control the steam temperature. If we're doing that, then the temperature of the effluent and the temperature of the tube wall will be whatever they will be. Alternatively, we could use the steam pressure to control the temperature of the tube wall. And if we were to do that, the steam temperature and the process fluid temperature would be whatever they're going to be. The most logical choice would probably be to use the steam pressure to control the effluent fluid temperature. And if we do that, then the steam temperature and the tube wall temperature will just be whatever they're going to be. Since we have only one manipulated variable, we can pair it to only one of our three output variables as a controlled variable. This method of calculating the number of controlled degrees of freedom assumes that the number of controlled degrees of freedom is really equal to the number of manipulated variables. Because remember, in our model, the degrees of freedom are all represented by input variables to the model, and we said that the input variables should be assigned as either manipulated or disturbance variables. So when we subtract the number of disturbance variables from the number of degrees of freedom, we're really finding the number of manipulated variables. And here we said that one manipulated variable would be the steam pressure. However, for some processes, the number of control degrees of freedom is less than the number of manipulated variables. To understand why the number of control degrees of freedom might be fewer than the number of manipulated variables, consider the simple example of this mixing tank with a bypass stream whereby the incoming stream 2 can bypass the tank. Based on the feedback control loop that you see here, the composition of the stream leaving the tank is being measured and controlled by manipulating the fraction of the flow in incoming stream 2 that gets split into the bypass. The question is, can the outlet composition X actually be controlled by adjusting the bypass fraction, which in this case is a manipulated variable because it has a control valve on it? Dynamically, this might look like a great idea. The effluent composition X should respond almost immediately to changes in the bypass fraction flow rate, because this bypass actually bypasses the dynamics of the tank. But at the steady state, if we were to write a material balance around this entire process, the composition X must still be equal to the total amount of the solute entering the system divided by the total flow rate through the system, W1 plus W2. That is, the composition of the stream leaving this process at the steady state is actually independent of the bypass fraction. In this case, we have a manipulated variable that has no impact on our desired control variable. It happens in this case because this stream splits and then is recombined. So it doesn't matter whether the incoming solute in stream 2 goes through this path or this path. Ultimately, it all has to come out in the end. So while changing F might change X dynamically, it cannot be used to change the new steady state of X. And we find that by writing the steady state component balance and seeing that F does not appear in this equation. The number of control degrees of freedom is the number of process variables that can independently be controlled. And again, this is usually equal to the number of manipulated variables, but it's possible that we could have manipulated variables that do not have an effect on a desired controlled variable, in which case that manipulated variable, like the F or bypass fraction here, does not represent a control degree of freedom. This can be understood more clearly when we begin pairing controlled variables and manipulated variables. We'll introduce this idea of pairing controlled and manipulated variables for a unit operation in subsequent videos.